MATH555 impulse functions. We have studied the differential equation with step functions, but there's another physical phenomenon sometimes we want to model. So you have an object moving on the table at some finite speed. This is your velocity, but at certain point you just hit it very hard, and it will suddenly increase. Right, the velocity will increase. Then it may decrease again due to the friction. But this sudden change is not something we can differentiate. So we cannot describe it by the differential equations very in the traditional sense. But we can say if you take the derivative of this function, you will see a spiking, right? Because you have a infinite change in finite. You have a finite change in infinitesimally small time. So the derivative of the acceleration is like that. And this function, because it looks like the shape of this delta, Greek symbol delta. So we call this delta function. Or you can say the delta function. So we can say the delta function represents the slope, the derivative of a sudden change. So let me define this formally. A delta function occurs at t0, if you plot it to look like that. And since it represents a sudden change, you have to say how large is the change, right? If the change is 1, then have a peak like that. If the change is 2, then the peak should also be doubled. Well, it's a little bit awkward to say that because the peak is already infinitely high. So double of infinite, you may say it's still infinite. So this is not really a traditional function. It's defined heuristically as the derivative of a step function. Like that. It takes derivative. But if you double the step function, you should also double the derivative, right? So a more rigorous mathematical definition is this. If you plot the function, you can say the area of this is 1. So the delta function, if you plot it, then the area is 1. Why? Because area represents the, this is the derivative, right? It's a change. I don't use this symbol. I use this, and this is some t is larger than t0, and this is less than t0, and then what's their difference? That's 1, right? So you can say the area of the delta function, the plot of delta function is 1. Okay, and but this still is heuristic because this delta function only has one point that is infinite. Everything else is 0. So a more useful property of delta function is this. If you integrate a delta function with a continuous function, then you can see it's just the function value at that point. Why? Because delta function is 0 everywhere except at t0, right, like that. But at this point, you have to multiply by the function's value. The function's value is f of t0, so you have multiplied this this point by that amount. So the integration will also be magnified by that from 1 to this. So that is, in some sense, the defining property of delta function. You integrate delta function times f, you get the function value at that point. Okay? And you can also say it in this way. If you multiply a delta function with a function, then you get a peak which is still at the same point, and the height is f of t. F of t0. So a delta function multiply a continuous function would just be another delta function. And this time it's delta function times the height of that function at that point. Okay, so you can say this and that, they are the two properties of delta function. All right, now let's see how do we how do we model things using a delta function? Say you have a motion that is continuous, then all of a sudden you have a push. So your acceleration would be, let's say, in the beginning it's just let's say gravity, okay, negative g. Then at some point suddenly you have a push, so you have a delta function like that. All right, then let's see if you know where to start from and you know the initial velocity, then we can describe its motion in the future. And this physically it means your velocity suddenly increase by 1 at time equals 1. All right, so if you write down differential equations, you will see this equals the second order derivative of time, and this equals negative g plus delta of t minus 1. Okay, so how do we solve that directly? It means you have to solve this for t is less than 1. Then you get, let's say our initial condition is x equals 0 and x prime is also 0. Right, so it starts from still, then it's a free fall, right? So this x would be negative 1/2. It counts this as horizontal. Oops, sorry. Then you have this equals negative 1/2 gt squared. Right, and what is v? V equals x prime equals negative gt. And at time equals 1, v suddenly increased by 1. So v, we use this symbol. Before that moment, it's negative g. But after that moment, it becomes negative g plus 1. So your equation becomes the same. A, which is x double prime, equals negative g after that. But your initial condition for the second segment is changed. It becomes x equals negative 1/2 g, from here, t equals 1. And x prime at that moment is not negative g, it's negative g plus 1. So you solve this equation for t greater than or equal to 1, you get a solution. Alright, so you will have x equals, xt equals the starting position plus your initial velocity times the change in time, then plus, actually negative g times 1/2, then t minus 1 squared. Alright, so that's what you will get if you do it directly. You will get the solution is like this for t between 0 and 1. Then after that, this is your solution. Okay, this is for t greater than or equal to 1. Okay, now let's try to solve the equation using the Laplace transform. Say x double prime minus equals negative g plus delta t minus 1. And then your x0 equals 0, x prime 0 also equals 0. Okay, so how do we solve that? Well, we need to figure out what is the Laplace transform of t minus t naught. And that's easy. because according to the definition, that's just the value of this function at t naught. So that's it. So the integral, the transform of the other function is just exponential function with no extra term. So let's take that. The left-hand side will give you s squared capital Y equals negative g, not just g, right? Because after transform, you get this. Then for the delta function, you get e to the negative s times t naught, which is just 1. So that's it. So what is capital Y? Capital Y equals negative g over s cubed plus e to the negative s times 1 over s squared. All right. So what is your solution? This part is negative g times 1/2 t squared. If you remember, this will give you 2 over s cubed. Right? So you will get that. And this, well, here's the good thing. Although you have a delta function in your equation, your solution does not involve a delta function. That's because if your acceleration has an infinite value, your velocity will only change finitely, and your position will even be continuous. It's just to have a sudden change in velocity. So it's just a piecewisely defined. So this will give you step function instead of a delta function. Okay, so you will see this in step function. And what is that? So this will give you u1 of c, u1 of t. And how do we do this? This will give you t, remember? And the t will have to be shifted. So that's what you have. That's pretty simple. It's just this result. All right, let's see if it's the same as what we had earlier. So what does this mean? This means it's negative g half t squared when t is less than 1. And after that, it's negative half t squared plus t minus 1. Just like that, right? And this, of course, we know it's correct because, it agrees with what we had here. And how about after 1? It's this simple form, right? Let's see what we had earlier. It's this looks like something complicated. But if you expand it, you will see it should be the same. This will give you t squared minus 2t plus 1, right? And you see negative g half t squared is here. Then you have 1 times negative half g. So it's a negative half g and another negative half g. And this is 1 times that. It's positive g, so it's cancelled, right? Then you have negative g half times that. It gives you g times t. And here you have negative g times t, so it's also cancelled. So all you have is 1 times that, which is t minus 1. And that will have, yes, t minus 1. Okay? So you can see it's easier to do it in the Laplace transform. Alright? Now let's just do more examples. Sorry for that. What is going on here? Let's just go to new page. Let's see second example. Y double prime plus 2y prime plus 2y equals delta t minus pi. And y0 equals 1, y prime 0 equals 0. Okay, so the right hand side is just a delta function. It means it's almost 0 everywhere except at pi. So recall what we have, right? S y0 plus s squared y then plus 2 of negative y0 plus sy plus 2y equals, this is just negative pi s. Okay, and then plugging the values. Y prime is gone, and y0 is 1, 1. So you have negative s and negative 2. And you have s squared plus s plus 2. Sorry, 2s plus 2 equals e to the negative pi s. So you will have y equals s plus 2 plus e to the negative pi s over s squared plus 2s plus 2. Okay, so let's handle that. The denominator, if you write in a better way, it's s plus 1 squared plus 1. You notice if you expand the square, you will have s squared plus 2s plus 1. So it's a sum of squares instead of a factorization. Alright, so let's see. So you have s squared plus, s plus 1 squared plus 1. Then how about the numerator? Well, since we have s plus 1 here, let's split it. And we'll see why we split in a second. And then you have s squared plus s plus 1 squared plus 1 into negative pi s. Alright, now let's see. What is little y? You have s plus 1, right? That means you have a e to the at, and a is negative 1, right? Remember that shift? Then you have to do the inverse transform of replace everything by s. Okay? And this is just directly. You also have e to negative st, and do the inverse transform of that. Okay? And last term we'll do it similarly. But we'll do that a little bit later. Okay. This thing here. So what does this give you? E to negative t. And this one will be cosine of t. And then e to negative t sine of t. Alright, now let's deal with the last term. So you have the e to the negative pi s. So that means you have a step function. Right? Then what do? You want to do you remember the formula? You want to go the inverse way. So you find out the inverse transform. Then you replace t by t minus pi. And do we know the inverse transform is right here? Right? So you replace t by t minus pi. That's what you have. Okay? And that's your result. And if you want, you can simplify a little bit. If pi minus t, then this is sine of t with a negative sign, right? Because sine minus pi. So this is same as before. Cosine t plus sine t. Alright, so that's what you have. Okay. So that's it for the example. Let's see another example. Let's go to higher. And let's make the initial condition all vanish. Okay, so it's a fourth order equation. So we have to supply the initial condition for all lower order derivatives. And in this case, we make it all 0, so we don't have a lot of terms. Okay, we didn't do anything as high as third order before. Now we go to fourth order. How do we do that? Well, for Laplace transform, you don't need to worry much, right? Because it's very similar. It's if you do the transform, you get negative y0, then s y prime of 0, s square y double prime of 0, s cubed y triple prime of 0, plus s to the fourth y, then minus y equal the right hand side, which is negative pi s, not pi. Just negative s, right? Because t equals 1. And fortunately, all of this is gone. So you get y equals negative s over s to the fourth minus 1. So we're halfway done. You see, that's very efficient. But the other half is not so easy. You have to split. And this is right like that. And not enough, you have to keep going until you cannot split anymore. Oh, before that, let's do something different. Let's break them into two parts. Okay, let's call them A and B. So you want to add them together to make it 1, right? So you can see if you add them up, add them up, you get s squared. So you should minus them, right? So if you do minus, then what do you get? S squared plus 1 minus s squared minus 1, that is 2. So that's it, right? Then we split again. And 1/2 here. How do you split this guy? Very similar. S minus 1, S plus 1. And same thing, if you do minus, you will get 2 in the numerator. So let's divide it by 2 again. Be careful, don't get confused with this 2. This 2 is still there. And this 2 is still there. Okay. So what do we have? Okay, we're done with the partial fraction. Now we can just do the what's that called? The inverse transform. Or just write down what is y. Okay, this guy tells you that you have a u1 of t, and 1/2 is copied. Okay, to do this, you have to do the inverse transformation first, then shift t to t minus 1. Okay, so let's do this. This is negative, sorry, not negative, e to the t, right? And then e to the negative t, right? Then divided by 2. Then you have to, this is a sine of t. Okay, but we're not done yet because you have to replace every t by t minus 1. So that is your result. Okay, and if you like, you can write down this in terms of a so-called hyperbolic function. This is sine h of t minus 1. And this is sine of t minus 1. Okay, so that's your answer. And if you only have one step function, it means before 1, the function is 0. Okay, let's see. One more example. That example is a little bit abstract. If you solve this equation, okay, with the right hand side not really given, the initial condition is given, then you cannot really write down what is the solution, but you can write down in terms of f. Let's see what we get. Because the initial conditions are all 0, so you get y times s squared plus 2s plus 2. That's easy, right? and equals the Laplace transform is called f. So what is y? Y equals capital F divided by that. But that's it, because we don't know what is f. Well, anyway, let's just try that split. So you will have s plus 1 squared over 1. No, plus 1. Yes, right? So you will have okay. So let's see, how do we do the inverse transform? F over that, right? That is something. Let's go by definition. Sorry, not definition. Let's see. This is something called a convolution, which we haven't learned yet, but I explain to you. Suppose you have a function f of t, then convolute it with a different function. Let's call it g of t. That's defined as f of tau g of t minus tau, and integrate tau from 0 to t. Then you will have the Laplace transform of that equals 0 to infinity into negative st, and this is 0 to t f tau g of t minus tau d tau. Then you integrate over t, right? So you can see this. I can write down this as e to the negative s tau and e to the negative st minus tau, right? Because they add together to e to the negative st. And if you combine it with this f of tau and the g of t minus tau, then integrate over t, and then integrate over tau, you can do them separately, right? And what's the range of t and tau? Well, t is from 0 to infinity, and the tau is between 0 and t. So, oh sorry, this is not the. If you change this to t minus tau, then you can change it to 0 to infinity. And since t goes from 0 to infinity, and t minus tau also go from 0 to infinity. Okay. Well, this is not very rigorous. I should have done something more carefully to make it rigorous. But the result is just f of s times g of s. Okay. So that means the convolution will give us the product. Okay. So this is just f convoluted with the bottom is just e to the negative t times sine of t, right? You know, negative comes from here. So you have to convolute the function to get your answer, and then you can just plug in this into this formula to get your answer. But that's more of a theoretical interest, because convolution itself is another integral. But that's something we can say in general. Okay, And I think that's not required for the exam, and you can just know it for your knowledge, okay, for your interest. And I think that's it for this chapter, and we will review next time and have the exam. Oh, by the way, the exam is accumulative, so we'll have 2 reviews over chapter 6 and from chapter 2 to 3 and 5, and then we'll have the exam. Okay.